So in the last class we have solved some previous year problems. Mm, uh, Actually, how many of you in the last class, can you raise hands? Okay, fine, fine. So in the last class we have solved a few problems on the first law of thermodynamics and some from the properties of pure substance. And this time we will be taking some more problems from the previous year, and if any problem are there, so I will put my mail ID in the chat box. Any problem there in the previous years or anything in the related to thermodynamics, you can mail me. Okay. And from the next class onwards I would like to start some other subject. Okay. So I think it's time we can start now. Okay. So this is the 2020 set 2 previous year question. um, all of you have calculator along with you, right? Just respond someone. Hello.
Yes, sir.
Okay, okay. So I will wait for 1 or 2 minutes. You just read the question and try, and after 2 minutes I will solve. If all of you able to solve, then fine. We can skip, and you just tell me the answer. Otherwise, I will solve. Okay. So just read this question for 2 minutes, and then we'll start. Screen is visible, right? Hello.
Visible, sir.
So I will also read along with you.
Sir, in portal sessions are available, sir. Video.
It is starting. As of now, I think for the Tuesday it has been done, right?
Tuesday it's having
Yeah,
is it
yeah.
available.
Soon all would be available. Yeah.
Okay, sir. Okay. Thank you, sir.
So in a this question is from the properties of pure substance and especially from the Rankine cycle. Huh? I have. We will see this Rankine cycle more detail in the power plant part. Here we will just solve a problem. In a steam power plant, superheated steam at 10 megapascal and 500 degrees Celsius, it is expanded isentropically in a turbine until it becomes a saturated vapor. So here we will start with the TS diagram. Let's suppose this is the superheated steam, first point, and it expanded isentropically. It is expanded isentropically till it saturated vapor. This is our point 2. And after this, it is again reheated at a constant pressure to 500 degrees Celsius. So this is the 500 degrees Celsius point. So same point it will go. This is the third point. The steam is next expanded isentropically in the another turbine until it reaches the condenser pressure of 20 kPa. Let's suppose this is the 20 kPa line. So can anyone tell how you will decide, like after the expansion where it will be? Like it will be inside the dome or outside the dome? Can anyone respond? How will you find that?
Inside the dome,
How you decided?
because condenser the medium should be liquid for condenser.
it should not be like that, I think so. Another anyone? It should ideally it should be inside the air, but it may be outside, practically. So here, how will you decide like it would be inside or outside? That I'm saying. Getting my point or not? Hello.
Yes, sir. Yes, sir. By finding the dryness fraction.
1 minute, okay. So just we will drop this means it may here or here, anywhere it would be. So let's suppose it is the fourth point. So it is fifth and it is sixth. Can anyone tell me why we use this reheating here? What is the advantage of it? Anyone?
Sir, output is increased, then its efficiency will also increase. That's why we are using this rating.
So any other answer for this? You are saying like with reheating you can increase work output and efficiency both, huh?
Yes, sir. Yes.
Work output and efficiency, you are saying both. Okay. Any other answer? Work output increases. That's clearly we can see like here 1 to 2 and 3 to 4 both would be providing work, right? So any one?
Sir, mean temperature increases and that further increase the efficiency.
You are saying like mean temperature of heat addition, right?
Yes, sir. Yes.
No, no, no. Actually, what happens now?
Efficiency will decrease.
What?
Won't the efficiency decrease because of reheating?
Here actually in reheating what happens when we study in the power plant, that time I will show you in detail. Like in the reheating, efficiency will not increase. Efficiency will decreases, but work output increases. But another way you have read like regeneration process in the power cycle. So in regeneration, efficiency will increase. Okay, because here what you will be doing, like you will be using the energy what is associated here. So that you will be using. Okay, you are not wasting that energy. So in reheating only work output will be increasing. Okay, that keep in mind. Efficiency will decreases. Efficiency won't be increasing. Okay, because here anyhow you will be getting work output, but in the meantime you are giving also the in a heat to again you are providing heat, right? So what is the efficiency? Work output by q input. So you are increasing q input more, right? Here you are providing q. So that keep in mind for the heating. So here what they are asking like so now you have to find like work done by the both turbines together. So here what will be the net work done? W net H1 minus H2. This would be the work done for the first turbine here to here, and next turbine is 3 to 4. So plus H3 minus H4. So what is the value of H1? Anyone? One is here. What is the condition for one? 10 megapascal and 500 degrees Celsius superheated. So what would be the enthalpy at one? Hello.
That will be 3.
Your voice is breaking. Anyone can speak up? Hello.
So
3000.
enthalpy is 3000. 3370.
Okay. Now it is expanding isentropically till second point. So entropy would be the same from at the point 1 and point 2. So at the point 1 entropy is 6.5965. So it would be equal to the S2. So and we can it is the saturated vapor also. It is written here. Becomes a saturated vapor. So for the saturated vapor, it is the same value here only. 6.5965 and the pressure is 1 megapascal. So this pressure would be the from now on 2 to 3 pressure constant pressure line would be the 1 megapascal, and the enthalpy at second point would be this, right? Is it clear to everyone? If any doubt, then let me know. Okay. It is clear, right? Hello.
Sir, S1 is enthalpy of bed.
H1 is enthalpy at the inlet of the turbine 1. Okay. Starting condition 10 megapascal, 500 degrees Celsius superheated steam.
Okay. So, sorry, sir.
Huh?
Sir, S1, I think entropy
Acha, S1 is
wet vapor.
S1 is the entropy at the same here only.
Yes, sir.
Entrance of the here only. One this entropy we have taken, right? Hello.
Okay, sir.
S1 should be equal to S2, right? So now this is the 1 megapascal pressure we have got, and we will reheat till 500 degrees Celsius. So in the steam table we will see like 1 megapascal and 500 degrees Celsius enthalpy is this. So H3 we will be getting H3H 3478.4 kilojoule per kg. And now what I'm saying like that time, how will you find that the fourth point would be the inside the dome or outside the dome? Here only you can get. From now here, what would be the value of S3? What would be the value of S3?
7.7.
Hmm?
7.76.
2 1, huh? So it would be the equal to the S4, and condenser pressure is 20 kilopascal. So at the 20 kilopascal you can see 20 kilopascal you can see the like Sg entropy of the saturated vapor. It is 7.9085, and what we have value of 3 is 7.7621. So it would be surely inside the dome, right? Because it is here, and you are getting or not? Hello. Hello.
Yes, sir.
So now you have got like fourth point would be the inside the dome, and if the value of S3 would be the more than the saturated vapor entropy of the 20 kilopascal, then it would be the superheated zone only. Okay. That time you have to
Sir,
find.
how it comes?
Huh?
Sir, how it comes? This is this concept. Entropy at this is if entropy at 3 is less than the entropy at 4, then it will be in this liquid vapor.
I'm saying like this is the 7.7621. This is clear, right?
Yes, sir.
So we have expanded like isentropically, means reversible adiabatic reversibly we have expanded, and entropy of 3 point would be the entropy of fourth point, right? It is clear.
Yes, yes.
So S4 is also the S3 7.7621. Now this fourth point would be the outside the dome or inside the dome. How will you know? Now we have the value of Sg at this pressure, right? This pressure, condenser pressure, right?
Sir. Yes, sir.
So what is this value? 7.9085. So value of the entropy at the saturated vapor is more than the point S4, right?
Yes, sir.
So it would be the inside it, right? This point is 7.9, right? 7.9085. So 7.7 would be the inner side of that, right? It is clear or not?
Yes, sir. Yes.
So now how will you find the value of x? Formula I will write first. S4 would be the SF plus X SFG, right? Hello.
Yes, sir.
So let me know the value of
So,
x. S4 you have. S4 is this.
so 4 to 5, process 4 to 5 would be,
What?
hello. So the process 4 to 5 is in 1 bar pressure, isn't it? So from
20
the process
kPa,
1
na?
to
Not
2,
1 bar.
why did okay, oh, it's 20.
Getting or not getting? This is condenser. So sorry. Where is the this 4 to 5 process is the condenser pressure. So condenser pressure is the 20 kPa, right?
So then why did you take that H3 as 3478? It is corresponding to the 1 bar pressure, isn't it?
What
H3.
are you saying? 1 bar? You where 1 bar? 1 megapascal is there,
H3.
na? Not getting what 1 bar you are saying?
Okay. Okay, sir.
No 1 bar here, na? S3 would be the S3 should be equal to S4. So what would be the value of x from here? Anyone calculated?
Sir, 0.9793.
Any other
Yes, sir.
person?
Yes, sir. 0.97. 0.97.
Same.
97. Next 93.
9793.
So you have got the dryness fraction of this, and you can easily find the enthalpy of fourth point, right? H4 now. What will be the H4? HF plus X HFG. So you know now all values like HF is this and this value, and X you now know from here, and HFG. What would be the value of HFG? HG minus HF, right? Hello.
Yes.
So find let me know the value of H4.
Sir, 2560.88.
How much? 25.
60.88.
Yep. Now you have all the values. Like just confirm this value one or 2% more.
Yes.
Okay.
Same answer.
Okay, fine. So H1 you know, H2 you know, and H3 also we know now, and H4 also. So we can easily find the total work done, right, from here by both turbines. So what would be the value of W net? Just let me know, okay? H1, H2, H3, H4, all you knows. What is the answer? Let me know, okay? Hello.
Sir, 1513.02.
1513.02
02.
kilojoule per
W net is equal to turbine work minus condenser work.
what?
The net work output is equal to turbine work minus condenser work.
No. Here in question, what he is asking, it is asking like what the work done by both the turbines together. You need not to work about like a pump work. You have to consider nothing like that. Okay. And if you find the pump work also, now it would be only 1 or 2 kilojoule only. So both, what are the two turbines? 1 to 2 and 3 to 4. So you have to find the work done by only both these only,
Yes,
right? In this
sir.
case.
Yes, sir. I am getting this. 1513.0.
Okay. You are getting why we are not considering pump work here? Because in question it is not asked like find the net work done. So we can let work done net by the turbines T.
Yes, sir.
Clear? Any other doubt or we can go next question? So here main thing is to know like how to find most of things you know like 1, 2 and 3 points already we know the enthalpy and all, and we have to find how you can find the value of the fourth point. So that you have to keep in mind. Okay, you may commit mistake only that point. Okay.
Yes, sir.
Okay, sir.
So if it would be the like fourth point, maybe in some problem. 1 minute. Let's suppose in some problem it may come like this. Let's suppose fourth point come here only. Okay, one and second. Then how will you find the enthalpy here? Anyone? Second point. H1 you would be knowing. Known. Let's suppose S1 known. How to find H2? Anyone? Or after the class we can see. Hello? Because it may come right. If it is outside the dome, then you have to find like this only. Hmm? Clear or not clear? What? Hello.
Clear.
So how
Yes,
will you
yes, sir.
find? If you are not knowing, like let me know. Like I don't know, I will tell.
S1 equal to S2.
Okay. S1 equal to x2, S2. Then you will be knowing here, right? Value this you will be knowing SG. It is known.
So,
Okay.
sir, if we know SG, then we can calculate na. Then HG, we will also know.
What? Okay.
HG
HG.
will,
Here main properties you are knowing. So let me know. Okay. Accordingly tell. SG known. Okay. Then
so, sir, H2 will be HG plus
S2 will be. You just keep
uh,
on. I will say. I will hear. Say.
H plus Hg plus Cv ln of so this sorry T T2 minus T saturation
SG plus.
C yes T3 ln of yes sir it is T2 by it is T saturation T naught.
Okay.
Yes.
Okay. Same thing. TST we will write. So next.
Sir from here we can find T2.
Here you will know this, right? Known. After that T2 you will know. CP we will be knowing here. And
Then ln T2
uh,
minus this
okay.
T saturation
Yeah.
from
Fine.
there.
Okay. This way then you have to go. Okay. Everyone got it. If not got it, then we can tell. Like T2 you will know from here. And what will be the H2? H2 minus Hg would be the Cp. T2 minus T saturation. So T saturation already known, and T2 you will be knowing from here, and Hg is already given. So H2 you can find, right? Hello.
Yes sir yes sir.
Okay. So I will give. This is the same problem. Properties of pure substance we can also say, but it is in the RAC also. So vapor compression, VCRS cycle, vapor compression, refrigeration cycle. So some ideal cycles for according to application. So it is for the refrigeration ideal cycle for the refrigerators. Okay. So I will give some brief introduction to this, and then you will solve this. It is simply properties of pure substance like problem. Okay. So I have kept this here. So here also four processes are happening like this TS. So refrigeration would be the work absorbing cycle or work producing what?
Absorbing cycle.
Work absorbing,
Observing.
right? So here whole thing got reversed. Like initially it is like a clockwise cycle. Now it would be the anti-clock. Okay. So here we will start from here. Uh, let's suppose from here. Here it is the compressor. Anyone can tell what is the difference between pump and compressor?
Pump handles water.
Okay, pump handles liquid and compressor handles the gases, right?
Here,
Gases
yes,
we can say. So here it is saturated vapor, so it is like vapor only, right? Gas. So either it would be here or it would be in the superheated state somewhere else. So it means it would be the gaseous state. So compressor it is here. So one and it would be the isentropic compressor. Isentropic compression would be here. So 1 to 2, and after that uh, here it would be heat rejection, right? Because here to here it will go. If it will go this way, then it will be heat addition. Rankine cycle heat addition is here, right? This way. So here opposite to condenser means heat is rejected this way. So it is the heat rejection. So it will we will say condenser heat. It is the condenser because heat is rejected in the condenser only. So 3. It is the 3 point at the saturated liquid point. So from here uh, expansion will happen in the throttling valve here in the VCRS. That keep in mind. So it is the fourth point. So this is the compressor and this is the condenser and this is the throttle valve or expansion valve also we can say it is because expansion of gas will be happening here. So and 4 to 1. 4 to 1 is the what is this? Anyone knows?
Evaporator.
evaporator.
We can say evaporator or from here only cooling will happening. This is the refrigeration effect we can say. Evaporator. So whatever amount of heat is this, so this much amount it will take, and here we will be providing the work input. So what is the COP? In the initial classes we have studied like COP of the cycle. What is the COP?
H1 minus H4 upon H2
That is
minus
generally we
H1.
will write. After that we can easily write, right? So refrigeration effect by energy input, right? Hello.
Yes, sir.
So we will write the expansion here for all expressions for all. Like for the work input would be like H2 minus H1, right?
Yes, sir.
And heat rejection it would be H2 minus H3, and for the expansion valve it would be like H3 is equal to H4 because it is throttling. In throttling it is the isenthalpic process. So we know the properties for all and we can easily find the COP. So now read the question and try to solve in 1 minute. I will wait and after we'll start. Okay. If anyone has doubt, let me know. Otherwise, try. I will solve later. So here what it is saying, in the VCRS cycle, the refrigerant enters at the compressor in the saturated vapor state. So here it is saying like entering through the compressor in saturated vapor state at the evaporator pressure. So evaporator pressure, if here it enters to the compressor, from evaporator to it is going to compressor, right? So it is the at this point 1 with the specific enthalpy equals to 300 kilojoule per kg, means H1 it is given like 300 kilojoule per kg, and at the condenser sorry, in the compressor with a specific enthalpy 250 kilojoule per kg, sorry, it is 250, and the exit of the compressor is superheated at the condenser pressure. So exit of the compressor is this 2 with a specific enthalpy equal to 300 kilojoule per kg. This is the 300 kilojoule per kg. At the condenser exit, the refrigerant is throttled. Same thing. This is the exit of the condenser, so it is the throttled here. So H3 is equal to H4. To the evaporator pressure, the COP of the cycle it is given. It is 3. And the specific enthalpy of the saturated liquid at the evaporator pressure is 50. Means they have given the, this is at this point they have given enthalpy. H of A it is given like 50. Is the dryness fraction of the refrigerant at the entry of evaporator. Entry of evaporator is this point. Exit of the throttling. So you have to find the X at H4. Correct? Hello.
Yes, sir. Yes, sir.
So now COP you knows what is the COP here? COP would be what is the refrigeration effect? This one, H1 minus H4. And what would be the energy input? Energy input in the work given into the compressor. So means H2 by H2 minus H1. Now here we knows COP we know, and H1 we knows, and H2 also we knows, and H1 also knows. So from here you can easily find H4, right? COP is 3, H1 250, H4 we don't know, and H2 minus H1 is 50. So value of H4 from here 100, right?
Yes, sir.
So H4 it is came here. This value we knows. H3 also would be the 100, right?
Yes, yes.
So now you have to find what would be the dryness fraction at this point. Value of H4 you knows, HA you knows, H1 you knows, because HA is the HF and H1 is the HG, right? So now you can easily find H4 is equal to HF plus X HFG. So just try to solve. H4 is 100, HF is 50, X you have to find. HFG means HG minus HF. HG is 250 and HF is what? How much is HF? 50. So X will come as 0.25, right?
0.125.
Anyone have doubt? Here you have to know like what is the VCRS. Um, Initially that's why I have given some basic introduction to VCRS. Huh? But we will see like what is the effect of all other things in the RAC part. So here just you have to find. It is clear to everyone, right or not? Hello.
Yes, sir. Clear, clear.
Other people, any doubt?
No, sir.
Okay. Just read this question, the same question we have done in the class, right? So just 1 minute see and try to do. This is the, I think, some few years back previous problem. I forgot to write the year here. So just see. Same question we have did right initially, but it is in the theory part. So two identical metal blocks L and M, specific it is given, each having mass it is given, and the initially at 313 Kelvin, both temperature are same. So a reversible refrigerator extract the heat from block L and rejects to block M. So we will write make till L M. Here temperature will go 3123 to 293. So it is asking for like what would be the temperature of M block, right? How will you proceed? Anyone can tell? Hello, am I audible or not?
Audible, sir.
Yes, sir.
So any idea how will you proceed?
We can equalize MCP delta T of both blocks.
MCP delta T. Okay then. So you are saying like work input would be, let's suppose here from here it is Q1 and here it is Q2. So
Sir, can we apply entropy concept?
identical block L and M each having mass this initially at it is just opposite. Okay. It is this is reversible refrigerator and work input. This is L block, this is M block. Let's suppose it is extracting heat from L block, right? Its temperature decreases from 313 to 293. So 313 to 293. It is extracting from here and reaching to here. So 313 to what will be the final temperature. So someone is saying like let's suppose this is Q1 and this is Q2. So W would be the Q2 minus Q1, right? Hello.
Yes, sir.
Yes, sir.
So what would be the Q1? M we knows, M C we knows, M C delta T. Delta T also we knows, right? Delta T how much it is here? 20 delta T. The value of Q1 we knows, but value of Q2 we don't know, right? MC delta T here it is not clear. TF minus 313, right? Hello. Hello.
Yes, sir.
So you have to find like how you can find the value of TF. If you know the value of TF, then you can easily find what will the work done, right?
Yes, sir.
So it is written here like a reversible refrigerator. So wherever a reversible word will come, so then the entropy of whole universe would be zero, right? Entropy change. Entropy would be the constant for reversible processes. Huh? So
Yes, sir. Yes.
here two systems are there. So one is system M, another one is system L. So entropy change for the system L, we will write first mc ln. Let's suppose here its final temperature 293, right? Directly we will write 293 by 313 plus mc ln, and its final temperature we don't know, Tf, and it is same 313. So m and c also same for both, it is written here only. So mc ln 293 Tf by 313 whole square. So it is 0. MC would come here, and ln of 0 and it's 1. So 293 Tf by 313 square. So easily you can find Tf here, right? 313 square by 293. How much it is coming? Hello?
334.
334 Kelvin. So it is asking for the what would be the minimum work required for this process, for this operation. That also you can find here. Only it is asking for temperature, so 334 would be okay. But it is asking for if work input, minimum work input. That also you can find around, right? Because we know the value of Q1 and Q2 both. Correct or not? Hello?
Yes, sir.
Clear, right?
Yes, sir.
Okay. So it is also just a conceptual problem, but quickly you read and try in 1 minute. So okay, try, then we'll start. If anyone did, then let me know what would be the answer and how you proceed. First tell the answer and then we will tell. Trying, right? Hello?
Solving.
Okay.
60%.
Okay. One or more, some people try and
Yes, sir.
60%.
I am getting same.
okay.
Yes.
So now we'll start. Figure below shown the reversible. Here also same thing. Reversible heat engine it is same. So having heat interaction with the three constant temperature system. For the two, we can easily correlate, right? With Carnot cycle like efficiency we can make and do that part is easy. But three systems or four reservoirs it will come. Then we have to do only by only this way only. Delta S of universe would be 0. Now calculate the thermal efficiency of engine. Here we know the value of Q1 and Q2, but we don't know the value of Q3. Hmm? So now what we can do here, three systems are there, so we can simply write, and it is the thermal reservoir, so its temperature will be the constant. Okay, so its temperature will be changing, then we have to take just before we have did. Okay, so our system is the this engine. So heat it is given here, so 100 it is positive, this 50 is also positive, and it is negative. So 100 by 1000 it is in the Kelvin, so okay, so plus 50 by 500 minus Q3 by 300 is equal to 0. So zero point 0.2 is equal to Q3 by 300. So Q3 would be coming 60, right? Hello.
Yes, sir.
So it is 60 kilojoule. So work net would be 150 we are giving, 60 going out. So it would be 90 kilojoule. Efficiency of the cycle would be the W net by Q input. So W net is 90 and Q input is 100 and plus 50. These two are given to the system. So we have to take consideration of only these two. So 90 by 150. It is 0.6. Okay. Hello.
Yes, sir.
Same way it is, right? If anyone have did in some another way, you can let me know. Hello. Hello.
Yes, sir. In same way.
Can anyone know which cycle is this? Cycle name, anyone knows?
Linear cycle.
So, okay, what is the application of this?
Mm,
Actually,
not known.
it is the when we have something in the compressor, diesel, not, and PCRS, let's suppose. Hmm. Now we haven't seen about the Breton and other cycles. So, but in all these cycles, what is happening? These are work producing cycle, right? Hello.
Yes, yes, sir.
So these are work producing cycle, but you will see like in all these cycles, four processes are there, right? Correct?
Yes.
So one would be the compression, another one is expansion, and another one is heat addition Q in, another one is the Q rejection, right? These four things would be happening in all these, right? Hello.
Yes,
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 sir.
sir.
So in this cycle, uh, linear cycle, what is happening? Here only three processes are there. This is also work producing cycle. Okay, work producing only. But what is the problem? Difference between this work producing and this work producing is here only three processes are there. Here only three things happening. Like expansion will happen, heat input and heat rejection. No compression is here. Okay, you can see right here. Something will happen here. Volume. Constant volume means no compression, right? Hello.
Yes, sir.
Yes,
And here expansion is happening. So due to no compression is there, so its efficiency is very less. What happens in compression? In compression, we used to give the work to the provide some work to the our working fluid, and its energy tendency to do more work. It gets right. Whatever we are giving to our fluid, working fluid, and it got compressed, and then we heat input we give. So then its tendency increases to do work. So we get more work from that those cycles which have compression process in them. Here no compression is here, so its disadvantage is efficiency is very less. Why? Because here no compression process. In compression what happens? um, we takes generally what where compression we take low temperature low pressure, we do the compression. So what happens? Because here volume is also less and pressure is also less, so we have to provide less work input, and it is very dense here. So now we provide the heat input here. We provide the Qn. So now in a tendency to do work of that working fluid is very high. So now we can get high work output. So this is the importance of the compression. W input. This generally I showed, but in the IC engine I will show in more detail these things. Here I am showing like how it is different from these cycles. Okay, got it? Hello.
Yes, sir.
Yes, yes, sir.
Okay. So now we'll start our problem here. It is also came in the gate previous year. So first solve this problem. It is very easy. See and let me know which one.
C, option C is correct.
Another someone.
C. C.
Okay. So we can see like it is work producing cycle, right? Because it is clockwise in PV. So it should be the same in the TS also. So one option got rejected here only, right? It is anti-clock. And process 3 to 1 is the isentropic process. So 3 to 1 here it is showing isothermal, so it is also incorrect. And here also same thing. So only C is correct this way. And another we can say like it is constant pressure process and it is constant volume process, right? So the slope of the in TS curve dt by ds for constant pressure is less than dt by ds in constant volume. It is correct, right? Means slope of the
Yes, yes.
constant pressure curve is less than the slope of the constant volume, right? Hello. Hello.
Yes, sir.
Yes,
Ah. So we are 1 to 2 process is constant pressure curve, 1 2 to 3 is constant volume. So 1 to 2 is this and 2 to 3 is this. So this is the constant volume and this is the constant pressure. So we can easily see this is the correct. Okay.
Okay, sir.
So now do this part. This is the important part. Hello.
yes, sir. V1 is not given.
V1 you have to find it will not be given. Huh? You just try to do in 2 minutes and then we'll start. If anyone did, then let me know. Or if anyone like, what is the way to do this?
Sir, first we will find the gamma.
Gamma
This
is given, I
adiabatic.
think.
Sir, where it is given?
1 minute. Gamma
Yes,
it is
yes,
given.
yes. Given. Yes, sir. Sorry, sorry.
Okay, I'm just starting. So in between, I will ask what to do. Okay? You tell, then let me know. First part is clear to everyone, right? So what is the efficiency first? Two ways we can do, like W net by Q input, or same thing we can also write like 1 minus Q rejection by Q added, right? But here what you have to do, like you have to find the, it is cyclic process, correct. So for the cyclic processes and it is a closed system also, because it is used as the IC engine. So for the cycle net is equal to W net, right? Hello.
Yes, sir.
uh, two three ways same problem you can do. So one way W net, how can you find? You can find the work done from 1 to 2 and 2 to 3 would be 0 because it is the constant volume process, and what should the work done here. So W net you can find uh, W1 to 2 plus W3 to 1, and W2 to 3 would be 0, right? Hello.
Yes, sir.
So either this way you can do, or say in another way, this way also you can do. Here you have to find the work done, and next you have to find the heat rejection in the all processes. But if in this formula you will be using, you have to find only heat rejections only, means heat rate values you have to find. So this way also, this way you can easily quickly find. So q1 to 2 find, and q2 to 3 will you find, and q3 to 1 would be 0, right? Because it is isentropic, so adiabatic process, right? Q is equal to 0 here, and here w is equal to 0, correct? Hello.
Yes, yes, yes.
Okay, so we will start. First of all, we will find the what is the value of v1. Okay, so we know the value of p3 by p1 is equal to v1 by v3 to the power gamma, right? Here gamma we can shift here also, 1 by gamma. So p3 p1 we knows, or the so it would be the 4 to the power 1 by 1.4 is equal to v1 v2 v3 is 1, so v1 it will come. What is the value of v1 it is coming?
2.69.
0.3.
2.69. Next, oh, tell up to 4 digits. Okay, I use 2.6918
Yeah.
meter cube. So we know the value of v1 now. Now we can easily find, right? What is the W122? W122 is the constant pressure process. So constant pressure process is P V2 minus V1. So P is 100, V2 is 2.6918 minus 1. Hello?
Yes, yes, sir.
So how much it will be coming? 169.18. Correct? Kilojoule. Hello?
Yes, yes, sir.
Or it would be opposite, because 2 we have to write 2 first. Here I have written opposite. Okay, I have put 1 here, right? This is v1 and this is v2, correct? Or this way, 1 minus 2.6918, so it would be minus, right? Because it is here we are, what we are doing, we are compress at the constant pressure we are reject taking the we are doing the work here, right? Work in terms of work we have to say. So what would be the W223? It would be 0. And what is the work done from 3 to 1? It would be the P1 V1 minus P2 V2 upon gamma minus 1, right? Hello.
Yes, yes.
So all values you know, let me know how much it is coming. Q400
Sir, 327.05.
How much it is coming?
327.05 minus.
Minus it will come.
Plus.
Plus it will come, right?
Plus.
So W net how much? Just simply add all three works, it will come. Means simply subtract this, and because this is 0. So how much it will come in?
157.87.
Now we have to, now work we have got, now we have to find the heat interaction. You just tell me what are the values here. Here how much it is? 2.6918, right? Here it is 100 and 400, right? Hello.
Yes, sir.
Mhm. So this is PV to the power gamma is equal to constant. So now we will be finding like from Q1 to 2. So what would be the Q1 to 2? It is mCp T2 minus T1, right? Because it is constant pressure process, right? Hello.
Yes, sir.
Uh, so m and 2 3 formula you have to keep in mind here. Like Cp minus Cv is equal to R, and Cp by Cv is equal to gamma, right? Hello.
Yes, sir.
And when combine these two equations, though, then it will come like Cp is equal to gamma R over gamma minus 1, and Cv would be the R by gamma minus 1, right? Hello.
Yes.
So and because in this question we don't know the value of Cp and Cv separately, so we only know gamma here. So in terms of gamma we are trying to do. So we will put the value of Cp here, and Cp is the gamma R by gamma minus 1, gamma R over gamma minus 1, and temperatures we don't know. We know the pressure and volume. So temperature PV is equal to MRT we will apply here. So what would be the T2? P2 V2 by MR and minus P1 V1 by MR. So we can see like MR will got cancelled from here, M here and R here, right? So it will come gamma over gamma minus 1 P2 V2 minus P1 V1. Same way from Q2 to 3 we can easily find. How much it would be? MCV delta T, right? MCV T3 minus T1. Sorry, T2. Hmm? So M, how much is CV? CV from here we can take R by gamma minus 1. And T3, V3 by MR minus P2 V2 by MR. M and R will got cancelled. So from here how much it will come? 1 by gamma minus 1 V3 minus P2 V2. So just now let me know the values, how much it is coming. Here we V2 minus P1 V1. Gamma or gamma minus 1 just calculate, and this value we already know, right? What is this? This is W1 to 2, right? Hello? Hello?
Yes, yes, sir.
Just let me know the values from here, okay? What? How much Q12 is coming? How Q23 is coming? Now you can calculate, right? P2 is 100, V2 also knows 1, P1 V1 also knows, P3 V3 and V2 V2. All values knows, right? Someone is doing or not?
Hello.
Yeah.
Sir, instead of finding Q1 to 2 and Q2 to 3 again,
Mhm.
um, if we find Q2 to 3 and if we subtract it from the net work done, we will get Q1 to 2, right?
That also we can do, but you that same way you can do, because net heat interaction is the same way.
Okay.
But here with this way, I want to say, like, if you just calculated these two things, net work done also need not to calculate it, right? From here only you can find the efficiency, right?
Yes.
So
Yes.
that way you have to think of two ways. So I just try to tell everything here. So that's why I did first work done and then now this.
Okay.
So just let me know the values here, how much it is coming.
Q1 to 2, I'm getting 170.
1 minute. You want to do how much? 170. Any after decimal?
0.14.
And how much? What about this Q2 to 3?
328.64.
328.64. Hello.
Yes.
Any other same thing?
So I'm getting different values.
I think it would be different, right?
So I'm getting Q1 to 2 is minus 592.13 kilojoule.
1 minute. How much you are saying?
Minus 592.13.
It would be in minus, because PV2 P2 V2 minus P1 V1 is what? Simply this W12, right? Because this is what P2 and P1 is same. So P2 V2 minus P1 V1 is minus 169.18. So just simply it divided by this 1.4 by zero point 0.4.
I am also getting the same minus 592.1.
You can also
Answer Q2 to 3 is 750.
just correct this value, someone told wrong initially. So how much it is?
750.
Hmm. Okay. So you can easily now find the efficiency. 1 minus, sorry, first we'll do W net by Q input. So what is the W net? 157.87. and this is 750. So how much it is coming? Hello.
1%, sir. 21%.
21%, right?
Yes, sir.
So by this also you can find, right? Q rejection by Q addition. Okay, same it will come. So this is the analytical way how we can find the efficiency of linear cycle. Now the one can remember the formula also for same, but initially you may not, because with the processes if you will go then you can find. It may take time. So here we know, right? All the things are in the same way, like gamma minus 1, and if we convert this, so one thing. So here pressure ratio it will say like 1 P2 by P3 means this pressure. One is the constant pressure process, and then we increase the pressure. So RP will define as P3 by P2 or P1, right? Anything we can write. So RP will define here, and now efficiency is 1 minus gamma Rp to the power 1 by gamma minus 1 by Rp minus 1. So now if you find with this formula it is a bit easy, but you may not remember the formula. So this is the analytical method for the same, and this is the formula also you can get. Okay. Hello.
Yes, sir.
Now we'll solve one more problem and then we'll stop again. Just I will read first because it is big problem. So in the figure shown below, the system is pure substance. System is a pure substance kept in the piston cylinder arrangement. System is initially at a two-phase mixture containing 1 kilogram of liquid and 0.03, like it is saying, it is containing 1 kg of liquid and 0.03 kg of vapor. So it already it is said like it is mix of both. So at a pressure of this 100 kPa first. Initially the piston rests on a set of stops. So it is in the stops. Uh, at pressure 200 kPa, kPa is required to exactly balance the weight of the piston and outside the atmospheric pressure. So means when the pressure inside the system is 200 kPa, so it is in the equilibrium with the atmospheric surrounding pressure and the weight of this. So after that it will keep rise. So heat transfer take place into the system until the volume increases by 50%. So heat transfer, we will adding the heat from some outside body to system, and its volume increases by 50%. And heat transfer occurs in such a manner that piston, when allowed to move, does so in very slow mass motion. Means it is equilibrium. It is reversible process. Quasi static and quasi equilibrium it is saying. So the thermal reservoir from heat is transferred to the system has a temperature of 400. Means it is the, let's suppose this is reservoir at 400 degrees Celsius, in Kelvin will write. 673 Kelvin. And system boundary is taken as 175 degrees Celsius. The heat transfer can be heat transfer to the system is 1 kilojoule. So this amount it is given 1 kilojoule, during which entropy increases by 10 joule per Kelvin. So it is saying like entropy of the system is increased by this amount. Okay, it is not for the whole universe. So this is the delta S of system. So delta S, S for the surrounding is for this only this reservoir. Okay, so system we know, so easily we can find the delta S of the surrounding, right? Because Q knows, we know the amount of heat and we know the temperature here. So just see this part first because we are doing this seriously. So net entropy generation considering the system and the thermal reservoir together during the process is closest to. So surrounding we know 1000 joule by 673. So what would be the value of this delta surrounding? Anyone? It would be close to 1.5, I think.
1.485.
1.485. But from reservoir it is heat is coming out, so it would be the negative, right? Heat rejected by the reservoir it is, so it would be negative. So what would be the net entropy generation? Delta S of system plus delta S of surrounding. So we simply add, like it would be close to 10 minus 1.5, it would be the 8.5. Okay. Now coming to the it now what will happening? It is heat is given to the system, and it is said like at the 200 kilopascal it is in the equilibrium with mm, it is able to raise this piston opposite to this its weight and this atmospheric pressure. So no other constraint is there, so it would be simply we are adding heat and it will keep on rising. So its tendency to make the system at the same 200 kilopascal pressure, right? Hello.
Yes, sir.
So it is the constant pressure process, right?
Yes, sir.
So now you have to find like you know the what is the process to find the work, but initial volume and final volume if you get, then easily you can find how much work done we have to do. So now we are trying to do that. Initially it is the 100 kilopascal, and it's condition of the steam it is given, so we can easily find the dryness fraction here. What is the dryness fraction? Mv by Mv plus Ml, right? So mass of vapor is 0.03, and this is one. Sorry, this is 1.03. How much it is coming?
0.0291.
So now you can find the volume, initial volume V1. How much it would be? Vf plus x Vfg, right? So for at 100 kilopascal. So this is in the steam table it is given. So you can easily find, right? Vg you knows, Vf you knows, x you knows. So let me know how much it V1. And V2 would be the 50% more, means 1.5 times of V1. So let me know both value, like meter cube kg. Anyone calculate what is the value of V1?
Sir, V1
That's
is
0.00.
0.0038.
Yes, right.
0.0038, right?
And sir,
Yes, yes, yes.
V2 is 0.0057.
Okay. So no, we now knows the value of V2 also here. So V2 is the after the completion of the process. So this is our volume. So at the end of process, what with the pressure inside the system? 200 kilopascal, because at that pressure it is only raising. So at 200 kilopascal, value of Vg, what is the value of Vg? 0.002, right? And what the specific volume we are getting? 0.005. So it's more than Vg, right? So it will be the superheated vapor left in the system. It is the condition of the system it is asking, and in other it is asking no vapor left in the system. It is wrong. Liquid plus vapor, it is also not here. So mixture will exist at the dry state of vapor state. It is also not, so it would be correct here. So work done we can easily get, because it is the constant pressure process 200 kilopascal, and this is V2, this is V1. 200 V2 minus V1. Simply we can do and we get the answer. So question is easy, but you have to read first. It is if it is lengthy, then it would be easy. So how much it is coming?
Point 3.
0.3 it is coming.
0.4.
Exactly how much it is coming?
0.388. That is point 4. Yes.
So because you have to see, because options are very closer. So below there. So this way we can do, and actually we can do lot of questions, but it is not of any sense. So you can try, and if any doubt is there, you can. I will put my email ID here, so you can ask there. And from the next class onwards, we will start with the new subject.